Hello, Chem 2, and welcome to the last chapter of the 2020 season. We're going to deal with chapter 13, all about acids and bases, more specifically acid-base equilibrium. Our objectives for today is we're going to classify the Bronsted-Lowry acid or base and talk about the net ionic equation associated with that. You hear kind of noises in the background. I apologize. I'm upstairs in the studio, and I have the windows open because it's pretty warm outside, and so it's going to be a little noisy. My front yard is very small, and there's a road right out in front of it, so if you hear cars go by, that's what that's about. If you don't hear it, that's great. My microphone's working well and not picking up extraneous noise. Okay, so let's get to this. So we're only going to focus in this video on the first one, which is trying to define what a Bronsted-Lowry acid base is, and talk about how we can recognize an acid or base, and then what does an acid or a base do. So as is usual, your administrative pieces for this, there's an optional out, there's a required out, and they're going to be the chapter 13 exam. Do your best to get all that done before the end of the school year. I know it was really tight. We've only got a couple weeks left. Do the best you can to help you retain as much of the knowledge as possible. So, chapter 13, section 1, Bronsted-Lowry acid base. So first thing you got to ask yourself is, back in Chem 1, we very briefly talked about what an acid was. And as a matter of fact, at the beginning of this year, we talked about acids in regard to their ability to have a hydrogen. So what we did was we saw that an acid was any substance that had a hydrogen ion, the hydrogen cation, the H plus cation, as its only ion, and it had to be mixed with water. So for instance, HCl is not necessarily an acid unless HCl is dissolved in water. So example is HCl, when it dissolves in water, breaks up into hydrogen and chlorine. Notice hydrogen is the only plus, that makes it an acid. Sulfuric acid, when sulfuric acid dissolves in water, makes hydrogens and sulfates. Again, hydrogens are the only plus, so that's an acid. But sodium hydrogen sulfate, when it dissolves in water, it also creates some hydrogens. But according to Arrhenius' definition, that would not be an acid because it doesn't have that as the only cation. We'll talk about how that may need to change a little bit down the road. So what's a base? The base is the opposite. The opposite of the H ion is the OH anion, the hydroxide anion. Again, same logic. If it has an OH, then Arrhenius said that was going to be a base. So we have sodium hydroxide or barium hydroxide. If these guys were to be dissolved in water and break into their ions, they are going to create hydroxide ions. Therefore, they are bases. Now, let's talk about a reality check a little bit. When acids are put into water, they're going to ionize. And you see this, the double-headed arrow here. Some acids will 100% ionize, like the stuff we've seen on the previous slides, and some will reach an equilibrium. And actually, that's the whole point of this chapter, is those acids and bases that reach an equilibrium. But they're going to ionize in water. If they have this ionization and they have an equilibrium, then they can have an equilibrium constant. So you can have a KEQ. Now, one of the benefits to this chapter is our KEQs are going to be very predictable. Our KEQs expressions are going to be very predictable, because in the numerator, there's going to be hydrogen plus whatever the anion is that is left when you remove the hydrogen. And in the denominator, it's going to be the acid all the time. All ones, all the time. Hydrogen, whatever the anion is that's left when you remove the hydrogen, and the acid in the denominator. Now, because this is the KEQ for an acid, we give it a special term and special constant. It's called a Ka, meaning the KEQ value for an acid. So here's a bit of a reality check, though. When we think in terms of ionization, we think that hydrogen bromide, for instance, is going to 100% dissociate, and it's going to break into its ions, that it'll break into a hydrogen and a bromine. Well, let's think about what hydrogen ion is. The hydrogen ion is just a proton. And that seems pretty unrealistic that you would have a proton floating around in space or floating around in water by itself. So what it's going to do is it's actually going to react with the water molecules and make this H3O plus ion. You're not going to have the free proton, the hydrogen proton, as an entity in water. It's actually going to bond. You're going to have the two molecules, the HBr and the water, collide, typical reaction, and the hydrogen is going to leap from the HBr to the H2O, making H3O plus and Br minus. Same thing with the acetic acid at the bottom. You're going to react. There is going to be an actual reaction of the acid with the water, making the H3O plus, and that's called the hydronium ion. Now, with that being said, that's the way things actually are going to happen, but you'll often find people simplify and shorthand this process by still treating it the same way you see in the previous slides, where you just say it just breaks up. Because if I look back at this, you know that the number of H's you might determine would be the same number of hydroniums that are going to be made. So if this is an easier way to view this reaction and just counting the number of hydrogen ions as opposed to counting the number of hydroniums, from a calculation standpoint, it's exactly the same. So you're going to see this intermixed between the correct way to do it with the hydronium in there and the ones that are not. So our correct Ka, instead of having the hydrogen ion in the numerator, it's going to have the hydronium ion. But I'm still going to say, when we get to the next series of slides or next series of videos, you're going to see very often it's simplified to make it be the hydrogen ion, just for simplification and making this a little less clunky. So what's up with the other way to define or look at acids? So Arrhenius's definition, in all of its glory, has one very, very valuable component, and that is you can recognize an acid or a base by what it looks like. Bronsted and Lowry, two different scientists who were both working about at the same time in two different parts of the world, one was in Denmark, one was in California, they both came to the conclusion that a Bronsted-Lowry definition, it's not what it looks like, it's what it does. When a Bronsted-Lowry or an acid interacts with that water, what it's going to do is it's going to donate its proton to the water, or you're going to see in a little bit where you're always going to have the proton being donated to some other substance. In the case of just purely dissolving it, it's going to donate it to the water. So according to Bronsted-Lowry, an acid is something that donates a proton. So you'll notice sulfuric acid, when it reacts with water, if you think about it, one of the H's from the sulfuric acid is going to be transferred to the H2O, leaving you with hydronium and the hydrogen sulfate ion. So because the sulfuric acid H2SO4, when it is mixed with water, the hydrogen ion, the proton, moves over to the water. It is donating its proton to the water, therefore it is an acid. So what would a base be? Well, acids and bases are opposites of one another, right? So a base would be maybe the proton acceptor. It's whatever substance is going to receive the proton. And this is where Bronsted-Lowry's definition actually has a lot of basis, is you don't have to have something that's necessarily only has a hydrogen. Long as it has a hydrogen and is able to give that hydrogen during a chemical reaction to another substance, then the donor is going to be the acid, and whatever substance, whatever compound receives it, whether it has an OH or not, is going to be the acceptor, and that's going to be the base. So for instance, in this situation, water is a base. Sulfuric acid, H2SO4, donates its proton to what? To water. So that makes water the base. Kind of interesting. I know back in Chem 1 and even to some degree in middle school, you talked about water being neutral. Water is neutral. Water is neutral. Water has a neutral pH. Water is a neutral substance. But according to Bronsted-Lowry's definition of what acids and bases are and how they act, the fact that the water can accept the proton says that the water is going to act like a base. Water can receive the proton. So what that leads to is an interesting phenomenon, and that's called conjugates. And we're going to touch on it very, very briefly here, but trust me, if you guys choose to come to AP, this is a big, big, big piece of a whole other facet of acid-base and special equilibrium, the conjugates, but I wanted to address it real quickly because let's think about it. Let's go back to this reaction. This reaction is written as being a one-directional reaction, where in fact it's an equilibrium. So what substance going backwards is the acid? What substance going backwards is going to donate its proton to the other substance? It's going to be the hydronium. Hydronium is going to donate its hydrogen. So going backwards, hydronium is the acid and hydrogen sulfate is the base. So when you have an equilibrium, you have a forward acid base and a reverse acid base. The ones that are on the right-hand side as the reaction is written are called conjugates. So from the standpoint of our example, okay, the acid is sulfuric acid. Its conjugate base is hydrogen sulfate. It only differs by the removal of the proton. So sulfuric acid has a proton removed, so it becomes hydrogen sulfate. That's a conjugate acid-base pair. And then you've got water is receiving a proton, so its conjugate acid is the hydronium. So you actually have what are called conjugate acid-base pairs. Two substances in a equilibrium that differ only by the presence or absence of a proton. In our example here, one conjugate acid-base pair would be the sulfuric acid with the hydrogen sulfate, and the other conjugate acid-base pair is the water with the hydronium. Two conjugate acid-base pairs, they're combinations of substances that only vary by one proton. And again, come to AP, we're going to talk a lot more about what these things do and how they're special, but there's a really, really cool specialness to these combinations of conjugate acid-base pairs that allow us to very adequately control the pH of a solution. Okay, now you may have noticed, or maybe not, that there may be some substances that act like an acid or a base. Water is the classic example. Water can gain a proton or it can lose a proton. Okay? Water can gain a proton by, like, say, this acid, this acetic acid in this situation is going to give a proton to the water, and now it's going to be hydronium, or the water can give a proton to, in this case, the ammonia, so water can act like a base. Any substance that can act like an acid or act like a base is called an amphiprotic or an amphoteric substance. Both of these words are used interchangeably. There's not a lot. It's anything you have that can lose a proton and gain a proton. Any substance that can do both is going to be amphiprotic or amphoteric. Again, if you come to AP, we're going to talk about a lot about some of these cool compounds that actually are amphiprotic or amphoteric, both of which are going to be kind of cool. So, one of the last things I want to address in this video is strengths. Not all acids go through equilibrium. There are some that do not go through equilibrium, and they're referred to as strong acids. Now, you think it's strong acids, you're thinking, oh my goodness, that's something that's going to burn me, it's going to hurt a lot, blah, blah, blah. That has nothing to do with the strength of an acid. The strength of an acid is solely about how dissociated the acid is when it's dissolved in water. So if it 100% completely, as far as we're concerned, completely dissociates in water, that's going to be a strong acid. So how do I know what acids are strong? Well, you just got to memorize them. There's the list. Hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid are all strong acids. Any other acid that's not on this list is weak, which means it undergoes an equilibrium. I'm going to say that one more time. These 7 acids are the only strong acids. Any other acid that is not on this list is going to undergo an equilibrium and therefore is going to be considered a weak acid. There are also strong bases, and again, I'm going to tell you, if you remember back, and I know this might be a bit of a stretch, when we were talking earlier on with solubility rules way back in the beginning of this class, there was a series of rules for the hydroxides and which hydroxides would dissolve. Well, it was group 1 plus calcium, strontium, and barium. All other hydroxides were insoluble except group 1 and calcium, strontium, and barium. Guess what you have here? Those are the strong bases. These guys will 100% dissociate. So if something is going to 100% dissociate, before what we did was we split it up when we wrote our net ionic equations, and we're going to do the same thing here. If an acid is weak, we're going to leave it together. If it's strong, we're going to split it apart. We've seen this before because we had to deal with strong and weak acids before. So it's the same exact list. Put it back in your memory banks. Life is good. So what types of reactions happen between acids and bases? Well, probably the most common is a neutralization, where you have an acid reacting with a base to make salt and water. And when I say salt, any ionic compound does not have to be sodium chloride. So for instance, nitric acid can react with sodium hydroxide. Nitric acid acts like the acid, sodium hydroxide acts like the base, and it reacts to make sodium nitrate, which is a salt, and then water. The H from the acid and the OH from the base come together and make water. And that's it. What we're going to do next is we are going to focus in our next video on some of the applications of the pH scale. So until then, everybody stay safe, stay happy, practice that social distancing, and I'll see you on the next video. Sig figs do matter. Toodles.